In this video, we'll talk about asymptotes of rational functions and how to find them. Let's start by taking a look at vertical asymptotes. Vertical asymptotes occur in rational functions, which are defined as a division of polynomials, when the denominator is equal to 0. Note the problem occurs there because the function would not be defined, and something interesting happens when we actually draw the graph, as we can draw this sort of imaginary boundary for the vertical asymptotes. So we can easily find them whenever the denominator of the rational function is equal to 0. But there is a complication. We have to reduce rational functions before we can find all the vertical asymptotes, because the factors that do happen to reduce, they actually do not give a rise to a vertical asymptote. It's simply not strong enough because the factor sort of like disappears, and actually all we get is a hole in the graph. So we don't actually get this boundary um, that's defined to be a vertical asymptote. So let's take a look at our first example. Here is a rational function, y equals to x plus 1 over x squared plus 5x plus 6. Let's try to figure out if we can reduce it. We can actually factor the denominator as x plus 2 times x plus 3. Note that there are no factors in common. They have to be exactly the same factors to be able to cancel any of them. Since we can't do that in this case, that means we can't reduce any further, which means also we can proceed to find vertical asymptotes. And to do that, let's set the denominator equal to 0, which we do right here. Since we already know how to factor it, it's x plus 2 times x plus 3 equals to 0, which means we can simply set each factor equal to 0, and we get two zeros, x equal negative 2 and x equal negative 3, and these are actually also equations of the vertical asymptotes. Do not forget your x equals to, because this is the equation of the vertical sign. So it would be x equals to negative 2 and x equals to negative 3. Now note, this function had two vertical asymptotes, simply because this was a degree 2 polynomial in the denominator. Let's take a look next at horizontal asymptotes, which have a different reason behind them than vertical asymptotes. In fact, entirely different. When the vertical asymptotes arise whenever the denominator is equal to 0, the horizontal asymptotes is basically we try to figure out what happens to y as x gets either very big or very small in a negative perspective. In mathematical language, it would be x goes to infinity or negative infinity. So, how do we figure out what happens to y? Well, here is sort of a shortcut, or this is what happens when we get different cases or different situations. We can simply compare the degrees of the top polynomial versus degree of the bottom polynomial. And there are three cases that actually occur in this case. In case 1, what happens when the degree of the numerator is strictly less than the degree of denominator? Well, in this case, when x gets very large or very small in the negative perspective, then the denominator sort of takes over. That means the whole function gets very small, which we sort of say as y tends to 0. And because the function gets very small, that means y is equal to 0. Let's put 0 right here. So y equals to 0. And this would actually be a horizontal asymptote. So whenever the degree of the numerator is smaller than degree of denominator, the horizontal asymptote is y equal to 0. So what happens when the numerator and denominator, whenever the degrees are equal? Let's take a look at the second case right here. So if they're equal, let's take a look at the example. If y equals to 2x minus 5 over 5x plus 1, note that both top and the bottom have degree 1, which means the degrees are equal. So what happens? When the x gets very large, let's say 5 billion, then -5 and +1 are sort of inconsequential. So what do we get left? Well, when x is really big, all we get left is the leading terms, which would be 2x over 5x, right? So how can we reduce this? Well, notice we can actually cancel x and top and the bottom. So all we get left is 2/5. Take a look. So 2 over 5. So y equals 2 over 5 would be the asymptote. And basically we can actually figure this out. Y equals to leading coefficient of the numerator, which was 2, divided by leading coefficient of denominator, which was 5. So we get some kind of a non-zero value for the horizontal asymptote. So you may ask, what about case 3? What happens if degree of the numerator is actually larger than that of denominator? That would be the third case. Let's take a look at this next. So if degree of the numerator is larger than that of denominator, then there is actually no horizontal asymptote. But there is something that occurs specifically when the degree of the top is 1 larger than degree of the bottom. Then we get something that's called an oblique or slanted, not quite horizontal, but it would be slope that's non-zero. M slope that does not equal to 0. That's what we mean by oblique. And whenever the degree of the top is 1 larger, so we do get an oblique asymptote in this case. And it does play a role on the graph, so we still have to find it. So let's take a look. We can actually simply find it by performing long division. Let's say, here is an example. F of x is equal to x squared plus 2x plus 1 over x minus 1. And the goal is to find asymptotes of this function. So let's take a look to see what we can find. A vertical asymptote, simply we'll put VA, would be, actually let's see if we can reduce it before we can do it. I don't think we can. The top factors as x plus 1 times x plus 1 divided by, x minus 1. Notice we can't factor anything. So to find vertical asymptote, we simply set the denominator equal to 0, which means x equals to 1 would be the vertical asymptote. Now to be able to find the oblique asymptote, we actually need to perform long division. Let's take a look. So there is no horizontal asymptote in this case. And why not? Because the degree of the top is actually larger than the degree of the bottom. Notice it's degree 2 on the top versus degree 1 on the bottom. But because degree of the top is 1 larger, we do have something that's called oblique asymptote. So how do we find it? Let's do the division. So what if we have a long division in this case, x squared plus 2x plus 1 divided by x minus 1. So how we do long division, we take the leading coefficient here, x, the leading term, and make it go into x squared. Well, that goes x times. Now we take x and we multiply back by x minus 1. So what do we get? X times x is x squared, and then x times -1 is minus 1x, or minus x. Notice we'll line them up here. Then we subtract, remember we're subtracting polynomials. X squared will cancel, but the term here we need to change the sign into a plus. It actually would be a plus here. It's a little bit hard to see, but yes, a plus. So it would be 2x plus x instead of, because it would be negative times a negative would be a plus. So we have to distribute the sign. So we actually get 3x that's left over. So 2x plus x gives us 3x. Now we repeat the same step. x goes into 3x, positive 3 times. So now we take this 3 and we multiply it back by x minus 1. So 3 times x would be, and by the way, here we need to finish up, we need to take 1 down. So it would be 3x plus 1. So now we do the step 3 times x gives us 3x. Now it would be 3 times negative 1 gives us negative 3. And again we subtract, the 3x cancels, but again the negative will make it into a positive. We'll make it into a plus sign. So 1 plus 3 would gives us 4, which is a remainder. But it's okay, even if we do have a remainder here, in fact we will every time we try to find oblique asymptote, the remainder is inconsequential. The oblique asymptote is actually the answer. It's y equals to x plus 3. This is actually our answer for the oblique asymptote. The remainder actually disappears because we still have to divide it by x minus 1. And when x gets large, the remainder will disappear. So this is the only part that matters for the oblique asymptote. And that's how we find it.